before I forget to. Okay, so you all should have taken your exam 1. I have started to look at those. They're looking pretty good so far, but I should have those grades out to you fairly soon, along with grades for homework 1 and 2. I'm going to work on that over the next couple days. In terms of homework right now, you have the ALEX module, I believe, called Algebra and Solving open. It is by far the biggest module of this unit. The ones following it are relatively small. And the nice thing about this module is if you haven't started yet, or if you have started, you'll notice that it is mostly algebra review. It is review from college algebra that is pretty much essential to this unit because a lot of this unit is solving trigonometric equations, very similar to things you practiced in college algebra. And it is doing something called trigonometric proofs, which is sounds scary, but it's just algebra. So that module is just for review to make sure your algebra skills are a-okay. That is due the 21st, which I believe is Thursday. I will have a homework out to you this afternoon that will be due Friday. And otherwise, just keep up what you're doing and everything should be good. Does anyone have any questions on anything? All right, then if nobody has any questions, I will go ahead and get started. Also, hopefully you all have the course packet. I don't know if you've seen my announcements about it, but it is available. Please, 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 please go buy it ASAP if you do not have it yet, because it will be very important for what we're actually going to start today, which is trig identities. And there is an entire reference sheet in that course packet with the identities you'll need, in addition to having the structure for the notes we're going to be doing, and it will be incredibly helpful to you. So please, 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 if you have not gotten it yet, it is $30 from the bookstore. Do that. Okay. So now I will share the notes. All right. Cool. Hi, Charles. What's up?
Is this, are you starting, so I got the course packet.
Cool.
Are you starting at a particular place in it? Can we reference it for this lecture today?
Yeah, I don't actually have the page number offhand, but there should be a page in the course packet that has these 3 exact equations. It is after the graphing stuff we did, page 57. Okay. Yeah.
All right, great. Thank you.
Yep. Cool. So we ended the last unit with graphing. If you remember these graphs of sine, cosine, secant, cosecant, and all of that, we're going to switch gears away from graphing a little bit for a while. We will come back to it in a much different context later in the class, but this unit entirely focuses on the algebraic side of trigonometry, solving equations, proving identities. So we're going to start in relatively familiar territory, actually, and just see if we can solve these 3 equations. So that's better. I'm going to just separate these out just to separate my work. There we go. Cool. So let's start with the first one over here on the left. I want to solve 8 cosine theta minus 4 root 3 equals 0. And I want to solve for theta, just like when we solve for x in an equation. This may seem a little trickier because the theta is inside a cosine, but we'll see that this is actually pretty familiar to us. So I want to get theta by itself, just like in normal algebraic situations. What I want to do is get everything to the other side. So I'm going to start by adding 4 square root of 3 to both sides. This gives us 8 cosine theta is equal to 4 square root of 3. I want to get theta by itself. So my next logical step is to divide both sides by 8, which gives us that cosine of theta is equal to 4 square root 3 over 8. And simplifying this fraction, we get that it is the square root of 3 over 2. Okay, so we now know that cosine of theta equals square root of 3 over 2. So the question we want to ask ourselves here, because we don't really know how to undo cosine, it's not like a square root where we can take a square root of both sides, or a logarithm where we know how exponentials work. We don't really know what to do here, but we can think about it. We want to know what angle theta has its cosine being square root of 3 over 2. Another way we can think about it is, if you remember, root 3 over 2 is a pretty fancy number from the unit circle. So we may be able to just think about the unit circle with this. The other way we can think about it is, on the unit circle, which angles have an x-coordinate of root 3 over 2? Well, the x-coordinate is, we know it's positive root 3 over 2, so that's probably about right here and about right here. And if you remember the unit circle, it makes these two angles. This is root 3 over 2 here, because this is root 3 over 2, and that is root 3 over 2 down there. No, this is about root 3 over 2 right here. And if you remember from your unit circle, if you've memorized these special angles by now, you'd know that these two angles where the cosine is root 3 over 2 are pi over 6 and 11 pi over 6. You may also have thought of this angle right here as negative pi over 6, but read the directions very carefully. We want to find all the solutions of the equations in this interval. We will only want the angles 0 to 2 pi. Because if you think about it, there are infinitely many angles coterminal to these two, but we only want the solutions in the principal interval. So be sure to read the directions very carefully when doing these, because sometimes we'll want more solutions. So in this case, negative pi over 6 would not be a solution because it is outside of our interval, but so instead of negative pi over 6, we'd write 11 pi over 6. Any questions? All right, think about the next one. Similarly, we want to try to isolate theta as much as we can. So let's subtract 1 from both sides. We get that 3, or root 3 times the tangent of theta equals -1. Divide both sides by the square root of 3. We get that the tangent of theta is equal to -1 over the square root of 3. Now, tangents are a little bit harder for me to think about than sines and cosines. I don't have them memorized as well, but I recognize that, okay, there's a 1 in the numerator and root 3 in the denominator. That probably means, because tangent of theta is sine of theta over cosine theta, that probably means that the sine of theta was 1/2 in some fashion, and that the cosine of theta was root 3 over 2 in some fashion. Notice that this tangent is negative though, which means that the 1/2, the sine, and the cosine had to be of opposite signs because we have a negative fraction. So we had to have a negative divided by a positive, or a positive divided by a negative. If you remember the quadrants where the sine and cosine, i.e. the x and the y coordinate, were opposite, just drawing this out. Those occur in quadrants 2 and quadrant 4 because they have the same sign here and the same sign here, which would make the tangent positive. So we need to look for the cases where the sine is plus or minus 1/2 and the cosine is plus or minus root 3 over 2 in quadrants 2 and quadrant 4, because that is the only place they have the opposite sign. Therefore, the only two quadrants where that tangent could be negative. So if you remember your unit circle, there's this angle here where the sine is 1/2 and the cosine is negative root 3 over 2. And there's this angle here where the sine is negative 1/2 and the cosine is positive root 3 over 2. And these angles are 5 pi over 6 and 11 pi over 6. Again, that is just knowledge from the unit circle. So those are our two solutions here. Remember, technically, negative pi over 6 also works, negative 7 pi over 6, but we only want them in the principal interval for now, so we just leave it as these two. Questions? Okay, then let's do one more. We have 2 sine theta minus 1 equals 1. Let's add 1 to both sides, so we have 2 sine theta equals 2. Just trying to get the thetas by itself as much as we can. Now we want to divide both sides by 2. We get the sine of theta equals 1. So we want to think about angles in which its sine, i.e. its y coordinate on the unit circle, is 1. Okay, well, the y coordinate is 1 right here. That is the only place on the unit circle where the y coordinate is 1. So if you remember, this angle, that's a very important one, is pi over 2. There aren't two solutions here. This is the only place on the unit circle where the y coordinate is 1. So there's only one solution in the principal interval, and it is theta equals pi over 2. Questions on these? Okay, so let's change it up just a little bit. These equations look really similar, but the difference is instead of finding the solutions in the principal interval, we want to find all possible solutions to the equation, which seems kind of impossible at first, but there isn't a nice way to write it. Okay, so first we want the places where the sine of theta is the root 2 over 2, i.e. we want to look for the thetas, the angles that have a y-coordinate on the unit circle of negative root 2 over 2. So let's just draw a picture to help us remind ourselves of the unit circle. It's always good to draw a picture. And here is, we want y-coordinates around negative root 2 over 2. So we know this angle and this angle. Okay, so in the principal interval, what are these two intervals? Well, we know that one of them is 5 pi over 4. And this guy over here, if you remember from your unit circle, is 7 pi over 4. However, this works too. This is a solution that is negative pi over 4. We also have negative 3 pi over 4 because we could go backwards to this one. We could go, if we go over to 5 pi here and then go all the way around again, that is 5 pi over 4 plus 8 pi over 4. That's 13 pi over 4. And if you think about it, we could just keep going around and around and around and around and around and think of infinitely many solutions. But obviously we cannot write down infinitely many solutions because that just doesn't make sense. It's not, we can't do that. We can't write down infinitely many things. We'd never be done. So what's a really nice mathematical way we could write this? Well, let's start by thinking about the 5 pi over 4 solution. We know that 5 pi over 4 works, and we know all angles coterminal to 5 pi over 4 work. How do we get those coterminal angles? Well, we could go backwards 2 pi. That's a coterminal angle. We could go forwards 2 pi, just to make a full circle around. That's a coterminal angle. We could go forwards 4 pi around, go around the circle twice. That's a coterminal angle. The key here is that we can just always go 2 pi around, and that will always make us a coterminal angle. So the fancy way we write this is that theta is 5 pi over 4 plus 2 pi times k, where k is an integer. And if you remember, an integer is just a positive or negative whole number, because we can't go half of a 2 pi around, because then that wouldn't get us back to 5 pi over 4. But any integer value, any negative or positive whole number we plug in for k, that will work. That will get us an angle coterminal to 5 pi over 4. It will land us at the exact same terminal side. So it would be a solution to our equation. How do we indicate that k is an integer? Well, there's some really fancy math notation for this. You've probably never seen it before, but you'll just have to, I promise it works. And how we do this is we just say k, and then we make this little e. It's a Greek epsilon technically, and it means an element of. And then we have this fancy symbol for the integers that is a z that looks, I should draw it a little better, that looks like that. All this says is that k, our little variable k, is an element of the integers. That is all that says. That's saying, okay, we have 5 pi over 4 is the principal angle in the principal interval plus 2 pi times any integer. And we have to say in our answer that k is an integer. Otherwise, we don't know what k is. K doesn't make sense. So when we're writing our answer, we need to specify that k is an element of the integers. Questions on that? Cool. So we have all the solutions there, but we know that's not technically all of the solutions. So we also need theta equals 7 pi 4 plus 2 pi k, all of the angles coterminal with 7 pi over 4. We can use the same logic going forward or backward, multiples of 2 pi to get to the same terminal ray, but also k is an element of the integers. And we don't need to write them separately like this. You could also just write theta is equal to 5 pi over 4 plus 2 pi k, comma, 7 pi over 4 plus 2 pi k, and then only once do you have to write that k is in the integers. Any questions? All right, then let's do the next one. I'm just going to erase this because it's in the way a little bit. All right, we want to solve 3 tangent of theta minus the square root of 3 equals 0. Let's get tangent of theta by itself. So add a root 3 to both sides. We get that 3 tangent of theta is the square root of 3, and that the tangent of theta dividing both sides by 3 is equal to root 3 over 3. Okay, this doesn't immediately look like any sines or cosines that we recognize, but I know we've seen this before. And if you remember that the square root of 3 over 3, we had to rationalize this denominator at one point. It's the same thing as 1 over the square root of 3. You get from one to the other by multiplying the numerator and denominator by the square root of 3 of this guy. So they're the same thing. So what does that mean? Well, because tangent is sine over cosine, that means that the sine of theta was probably plus or minus 1/2 in some fashion, and the cosine of theta was probably plus or minus root 3 over 2 in some fashion, because then the 2's would cancel and we're good to go. Okay, but what quadrant are we talking about here? Well, we have a positive tangent. Tangent is positive root 3 over 3. So what does that mean? It means that we were in a quadrant where the signs of the x and y values were the same. And by sign, I mean positive or negative. So what quadrants does that occur in? Come on. Well, we know what happens in the first quadrant. We know it does not happen in the second quadrant. It does happen in the third quadrant, but not in the fourth. So we are looking at quadrants 1 and 3 here. Okay, let's draw ourselves a picture. Which angles have a sine of 1/2 and a cosine of root 3 over 2? Well, we know this one does. They're both positive, positive 1/2, positive root 3 over 2. And same here, we have same thing here, except they're both negative. We know this is a negative 1/2 and this is a negative square root of 3 over 2. So if we remember from our unit circle, these angles we are looking at are pi over 6 and 7 pi over 6. Now, we could write our answer very similarly to how we wrote the last one, and it would technically be correct. And let me show you what I mean by that. We could say that the answer is theta equals pi over 6 plus 2 pi k, where k is an integer, and that theta equals 7 pi over 6 plus 2 pi k, where k is an integer. This is not wrong. There is nothing wrong with this. It's the same thing. It's okay, here's pi over 6, all the angles coterminal to it just by going around multiples of 2 pi. And here's 7 pi over 6, and all the angles coterminal to it with multiples of 2 pi. But there is technically a better way to write this one. If you recall, just by looking at it, we can see, okay, pi over 6, what's the difference between pi over 6 and 7 pi over 6? It's pi. It took us pi to get from pi over 6 to 7 pi over 6. Okay, now let's go from 7 pi over 6 back over here. That took us pi. Okay, pi, y, okay. And then pi again, pi again, pi again. It only takes us multiples of pi to get from one to the other. Whereas in the first example, there were not even jumps between the two terminal rates. So we had to keep them as separate equations because there was no nice way to combine them. However, we don't need to write these as two separate equations, each with going around multiples of 2 pi. We can just jump from one terminal rate to the other by going around the unit circle pi radians. So the cleaner way to write this is theta equals pi over 6 plus not 2 pi k. We don't have to go around full circles of 2 pi. It only takes us pi to jump from each terminal side to the next. So it's pi over 6 plus pi k, where k is still an integer. And this is the most correct answer. The first one is not technically wrong. However, there's a much nicer way to write it, and this will be what is counted as the most correct on things like homeworks and exams. Because half of algebra is simplifying, and this is just basically a version of simplification. Any questions on why that works? Okay, let's do the last one then. We want the cosine of theta plus 1 equals 0. Let's just subtract 1 from both sides, simple enough. That gets us that cosine of theta equals -1. So we want angles whose x-coordinate on the unit circle is -1 because cosine is the x-coordinate. That occurs right here. This is the only place on the unit circle that has an x-coordinate of -1. And what angle is this? That means that theta on the unit circle is equal to pi. Okay, that's the angle in the principal interval. Cool. However, we need all of the solutions. So how do we write all of the solutions? Well, we just need to keep adding multiples of 2 pi to that because it is the only solution. There will be no fancy simplification. So all this one is just that our angle theta is equal to pi plus 2 pi k, where k is an integer. Questions on this idea of finding all solutions to an equation? All right, let's ramp it up a notch. I want to find all solutions to this equation right here. Tangent of x times cosine of x minus 4 equals 0. Now this looks really scary at first because, oh my God, there's a tangent and a cosine in the same equation. What are we going to do? And I know a lot of your first instinct is, oh, we could just distribute here, but we don't want to do that because it's already in a very nice simplified form for us. If you remember from college algebra or maybe even high school algebra, we would have to solve things like this. And if you remember, how would we solve something like this? Well, we know that one of these two things is 0. So all of the solutions are wherever we could make this factor and or that factor 0. So to solve this kind of thing, what we would do is set x minus 3 equal to 0 and solve for x there. We would get that x equals 3 and set x plus 2 equal to 0, where we would get that x equals -2. And those would be our two solutions because those would be the two things we could plug in for x that would make this guy right here 0. Now ours looks a little scarier because there's trigonometry involved, but it's the exact same idea. We could even put this in parentheses if it makes our eyes happier. We have this factor here and this factor here, and we know that anything that makes this 0 or anything that makes this 0 is a solution. Well, and anything that makes that 0, because only one of these two things needs to be 0 for the entire thing to equal 0. So to do that, what we need to do, we need to set tangent of x equal to 0 and cosine of x minus 4 equal to 0. Solve those for x, and then that's our solution set. So let's start with tangent of x equals 0. We know that tangent of x equals 0. Think about sine x over cosine x. We know that that's usually 0 over 1. Remember, it's never 1 over 0 because that is a mathematical no-no. That does not equal 0. That does not exist. So it's going to need to be 0 over 1, which means the sine is 0 and the cosine is either +1 or -1 because it doesn't matter which it is. 0 divided by any number other than 0 is going to be 0. So what does this look like on our unit circle? Where is the sine 0? Well, that happens right here and right here. So our solutions here, we want them in the interval closed 0 to open 2 pi. So that means it includes 0 and not 2 pi. So our solutions are x equals 0, comma pi. Again, 2 pi is technically a solution because that angle right there is 2 pi, but we're not including 2 pi in our interval, so we don't care about 2 pi. Okay, so those are solutions. Now let's think about the other side. Cosine of x minus 4 equals 0. Adding 4 to both sides, that means that the cosine of x is equal to 4. Okay, where on our unit circle, i.e. the circle with radius 1, is the x coordinate 4? I hope you feel like this is a trick question, because it is. There is no place on the unit circle where where our x coordinate is 4. The most the x coordinate ever gets is 1, because the circle is radius 1, and the cosine tells us what the x coordinate of the angle on the unit circle is. So this actually has no solutions. There is no way, there is no x value, there is no real number we could plug in for x to this factor here to make it equal 0. So the solutions to the entire equation, to this entire equation, are x equals 0 and pi. On the principal interval, of course. Any questions? Okay. Let's do another one. This one looks a little trickier, but it's very similar to what we just did. And now it's thinking about something called a trigonometric quadratic. We don't really use that word because we don't really need to, but if you recognize it, we have tan squared x. You saw stuff before like x squared minus 3 equals 0. Same idea, except now we just have that tangent to deal with once we have dealt with the quadratic. Okay, so I want to get tangent x as by itself as possible. So the first natural thing to do would be to get that 3 to the other side. Now, if you recall, just as a little side note, that the tangent squared of x, this is just notation for tangent of x squared. So what we're able to do now is take the square root of both sides, and that gets us that the tangent of x is equal to plus or minus, you always have to put a plus or minus in front when you're taking a square root of 3. So what do we want to know? We want to know all of the angles x on the unit circle in that principal interval where its tangent is square root of 3, positive or negative, it doesn't matter. We're probably going to be thinking about all 4 quadrants this time. So when does this happen? Well, you can think of this as being square root of 3 over 1, which indicates to us right away that we're looking at sine of x over cosine of x is probably root 3 over 2 in some fashion, plus or minus, over plus or minus cosine would be 1/2. That would get us a tangent of square root of 3, because this is just a really fancy way to write the plus or minus square root of 3. Okay, so now thinking about our unit circle, which angles have a sine of plus or minus root 3 over 2 and a cosine of plus or minus 1/2? Well, I know this angle right here does. This is pi over 3, because this right here is root 3 over 2, and this is 1/2. I know this angle does, because this is root 3 over 2, and this is negative 1/2. That's 2 pi thirds. This angle does right here, because that is a negative root 3 over 2, and that's a negative 1/2. And this angle is 4 pi thirds, if you remember. Lastly, there's also this angle right here that has it, and this has a y value, i.e. a sine of negative root 3 over 2 and a cosine of positive 1/2. This angle is 5 pi thirds. Now, just to separate my solutions a little bit, we know that the tangent will be positive in the first and third quadrant. So these two angles are solutions to the tangent is positive square root of 3. And we know that the tangent would be negative square root of 3 in the second and fourth quadrant. So those two solutions go together. Cool. So that'll be useful to us in the next part where we're finding all solutions. But for now, in the principal interval, we know our solutions are pi thirds, 2 pi thirds, 4 pi thirds, and 5 pi thirds. Beautiful. Okay, so now we want to find all solutions to the equation. We're dealing with 2 cases. First case is where the tangent of x is the square root of 3. And the second case is where the tangent of x is the negative square root of 3. So when the tangent of x is positive square root of 3, we're following this pink line on the graph right here. And we see, okay, so our first solution is pi thirds. We could separate them by writing pi thirds plus 2 pi k and 4 thirds plus 2 pi k. However, notice that from pi thirds to 4 pi thirds, it takes us pi to go around. From 4 pi thirds back to this terminal side here, which would be 7 pi thirds. It's another pi, 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 pi. So instead of writing two separate equations, like the problem we did before, we can actually combine this into one equation where we get that our x value is equal to pi thirds plus pi k, where k is an integer. Gotta keep doing that. Okay. Where k is an integer. Beautiful, because we're just going around by multiples of pi. We don't need to separate them into two. Tangents usually work really nicely this way. That is the case where you'll see a simplified equation more. Sines and cosines and are usually a little bit nastier. But tangents, we can usually nicely combine them like this. So this is our first solution. Similarly, with the tangent of x being negative root theory, we know that happens at 2 pi thirds, again at 5 pi thirds, which is pi away, then again at 5 pi thirds plus pi, which is 8 pi thirds, and then again 11 pi thirds. Again, just going around and around and around and around. We're going around by multiples of pi. So instead of writing two separate equations for the two separate angles, we can combine it into one and say that x is equal to 2 pi thirds, just using the first angle because it's convenient, plus pi k, where yet again, k is some integer value. Questions on this problem? All right, let's amp it up a little bit more and then we'll start to get into something called trig identities. I want to find all solutions of this equation in the principal interval, and then again, I want to think about all the solutions. So this one looks even scary. We have a 2 cosine squared, we have a cosine, we have 3. What does this kind of look like though? What if I replaced every time it said cosine of x, what if I replaced that with a u? So then we're looking at the equation 2u squared plus 7u plus 3 is equal to 0. We all should have seen this before, and this is a quadratic equation. This is something we know how to solve. So how do we do that? Well, there's many ways. You could use the quadratic formula. You could use the AC method of factoring. There's many ways to factor, and you'll actually get practice with this in ALEKS. But I'm going to use the AC method just really quickly. I know that A times C, 2 times 3 is equal to 6. And then I know that 6 times 1 is equal to 6. Adding these two, 6 plus 1 equals 7. So I know I want to break my middle term here, my 7 cosine x, into a 6 cosine x and a 1 cosine x, because I want them to add to 7. So 2 cosine squared x plus 7 cosine x plus 3 is equal to 2 cosine squared x plus, I'm just going to break up that middle term so I can factor by grouping, plus 6 cosine x plus cosine x plus 3. Now I have this group here and this group here. I want to pull a common term out of here. And so that gets us the common term here. I see there's a 2 cosine x in both this term and this term. So I'm going to pull it out to get us 2 times the cosine x times cosine x plus 3, and then cosine x plus 3. So I now have this. Oh, there's supposed to be a plus sign here. My bad. Okay, now I have this sum here. I have a common cosine of x plus 3 in both terms. So I can pull that out, which gets us to 2 cosine x plus 1 with the pulled out cosine x plus 3. So now we're in factored form. Again, if this is not as comfortable of a method for you, that is okay. You can use the quadratic formula, you can use whatever, and you will get lots of practice with this in ALEKS. And I will be going through some more later. So if that felt uncomfortable, it's okay. But just know that we have this factor and this factor. and that is going to be equal to 0. So what do we need to do? We need to solve both this factor and this factor for 0 to get all of our possible solutions. So we need to set 2 cosine of x plus 1 equal to 0 and cosine of x plus 3 equal to 0. I'll start by solving the one on the left first. Subtract 1 from both sides. We get that 2 cosine x is equal to -1. So the cosine of x is equal to -1/2. So on our unit circle, which angles have on the unit circle an x coordinate of -1/2? Well, I know that this one does and this one does. And if you remember, these angles are 2 pi thirds and 4 pi thirds, using a lot of unit circle knowledge here. And 4 pi thirds. Cool, those are 2 solutions. Now we want to solve cosine of x plus 3 equal to 0, which means that the cosine of x equals -3. Okay, where on the unit circle is the x coordinate -3? Well, never, because it is the unit circle, it has radius 1. The x coordinate will never be smaller than -1. So this factor here also has no solutions. So the 2 solutions in the principal interval are just 2 pi thirds and 4 pi thirds. Questions on that? Okay. Now just the last step, we want to find all of the solutions. Well, we know there's not really an even way we jumped around here. It took us 2 pi thirds to get to 2 pi thirds, and then another 2 pi thirds to get to 4 pi thirds. Then it took us 4 pi thirds to get back to that terminal right over here. So there's not really a nice way we can combine these 2 equations. So we do have to write 2 separate equations here. We just need to go 2 pi thirds and we need to go 2 pi k around, because there's no nice way to combine that. But we also know that we need every angle coterminal to 4 pi thirds. Don't forget that k is an integer. Questions here? Okay, now I'm going to start introducing those trig identities I was talking to you guys about, and this is the first set of them. And these are called the co-function identities. And the reason I'm presenting these first is because you've already kind of seen these intuitively and graphically a little bit, particularly with these 2 is what I have talked about. I've mentioned that every single graph of sine and cosine you can write as a phase with both sine and cosine, just with a different phase shift. Notice the cosine wave right here is just a shifted over version of the sine wave and vice versa. So if every single graph of sine and cosine, you could rewrite using these co-function identities. You could rewrite the equation of the graph just by adjusting the phase shift a bit. And that is all the co-function identities are. Similarly, we didn't ever really talk about this one because it doesn't make as much intuitive sense graphically, but it would make sense that that secant and cosecant are also co-functions, because their graphs stem from the graphs in sine and cosine. You drew the graphs of secant and cosecant from their reciprocal graphs of sine and cosine. So secant and cosecant are also co-functions. Similarly, tangent and cotangent are co-functions. In general, all you need to remember is this. If you can remember which pairs of functions are co-functions, the co-function identity does not change. Okay, let's practice using these a little bit. They look a little scary and they take a little bit of getting used to with using, but let's just try an example. I want to use a co-function identity to rewrite these expressions. So secant of 5 pi over 11. Well, what is secant's co-function? It is cosecant. So I know that the secant of pi over 2 minus x equals cosecant of x. I'm just going to write that down. Or that the secant of x is equal to cosecant of pi over 2 minus x. Cool. Just here, I know my x is 5 pi over 11. So plugging that in, I get that the secant of 5 pi over 11 is equal to the cosecant of pi over 2 minus 5 pi over 11. I just want to make a common denominator between those two so I can subtract them. So I know it's equal to the cosecant. The least common denominator I could use is 22. So multiplying this by 11, it's 11 pi over 22 minus 10 pi over 22. Just multiplying top and bottom of that by 2, which is the cosecant of 11 minus 10 is pi over 22. So using the cofunction identity, we were able to identify that the secant of 5 pi over 11 is equal to the cosecant of pi over 22. Cool, let's try one more. Tangent of 3 pi tenths. If you remember, the cofunction of tangent is cotangent, so the tangent of x is equal to the cotangent of pi over 2 minus x. In this case, our x is 3 pi tenths, so we know that the tangent of 3 pi over 10 is equal to the cotangent pi over 2 minus 3 pi over 10. Just making a common denominator, that means it's the cotangent 5 pi over 10 minus 3 pi over 10. 5 minus 3 is 2, so it's the cotangent of 2 pi tenths, which is just pi fifths. Questions on either of these or on how I used the cofunction identities? Just plugging in whatever angle was here for x. Okay. These are helpful to know and to have in the back of your pocket, and they're good intuitive checkers for why we can always rewrite graphs as either sine or cosine. If we're given any graph, we can always write it as its as the function or the cofunction. That's a good just reminder for why that stuff from Unit 1 worked. However, we're going to talk about some more important identities that you will use much more going forward in this unit, and that is the Pythagorean identities. And those are these three. This is the one you will see the most, but these two follow from it, and we will see why in a minute. Why are these called the Pythagorean identities? Well, let's look at the unit circle. If you remember, the Pythagorean theorem is just a squared plus b squared equals c squared. Right here, I've already done a little bit of work for us by saying, okay, a squared, I'm just going to say a is my x value, b is my y value, and c is the radius of the triangle, i.e. the hypotenuse, the long side. And because we're on the unit circle, excuse me, because we're on the unit circle, our radius is always just 1. And 1 squared is just 1. So I've already put a 1 there. Now on the unit circle, if you remember, what is the x value? Well, I've already said it here. The x value is the cosine of theta. The y value is the sine of theta. So when we plug them into the Pythagorean theorem, we get that cosine squared theta plus sine squared theta is equal to 1. Hey, cool. That's the first Pythagorean identity. It is literally just a fancy reiteration of the Pythagorean theorem using the unit circle and trigonometry. This will always be true, whether we're working on the unit circle or not. That is just a really nice way to set it up and to show that it works, but this will always be true. Now, the bottom two, I can look at my triangle and I don't really see why those work right away. I don't see tangents coming into play or secants, but let's do a little bit of algebraic manipulation. So I'm just going to rewrite that the sine of theta plus the cosine squared of theta is equal to 1. Cool. Now, I'm going to divide both sides by cosine squared theta. This may seem weird, but you'll see what I'm doing in a minute. And to do that, I need to divide all terms by the cosine squared of theta. Sine squared of theta over cosine squared of theta is just the sine of theta over cosine theta squared. And what's the sine of theta over cosine theta? It's the tangent of theta. So this first term, when we divide everything by cosine squared of theta, just becomes the tangent squared of theta. What's cosine squared theta divided by cosine squared theta? That's just 1. Anything divided by itself is 1. And what's 1 over the cosine squared of theta? Well, the reciprocal function for cosine is secant. So that is the secant squared of theta. And this is the same equation. It's a legal algebraic move to divide both sides of an equation by the same thing. So this is the same equation. Hey, look, it's identity number 2. Similarly, what if I, instead of dividing by cosine squared, decided to divide by sine squared? So I divide both sides by sine squared of theta, as I am allowed to do in algebraic manipulation. Sine squared over sine squared is just 1. Cosine squared over sine squared, if you remember, cosine over sine is cotangent. It is the reciprocal function of tangent. So this is just cotangent squared. And 1 over sine squared, the reciprocal function of sine is cosecant. So that is cosecant squared theta. Beautiful. That's it. That's where those 3 come from. You will probably use the top one the most, I would say, but you will need the bottom 2. Just know that if you know the first one, you will always be able to derive the second 2 in a pinch. These are also on your identity sheets. Every single thing we do that I call an identity will be on those identity sheets, and you'll be using them a lot. So I would get very friendly with them if you can. Questions on these? All right, let's put this into action a little bit. I just want to solve this equation. It's another trigonometric quadratic. Let's try to solve it. Oh crap, right away I notice I can't factor this. There's not, like in the first equation we did, or the first example, that was a cosine and a cosine, but now it's a tangent and a secant, and I don't really know how to work with that. I don't know how to factor that. That would be like if we were working just in college algebra or something, and we saw something like x squared plus y plus 2 or something. We can't factor that because x and y are not the same thing. What do I know so far that could make them the same thing? Well, I have some identities up here about squared functions. So maybe I want to do something with this tangent of square root of x. From my identities up here, I know that the tangent squared of x, or theta, plus 1 is secant squared of theta. I'm just going to make a note of that right here. But I don't have a plus 1 in here. So I just want to solve for what tangent squared of x is. And this is just manipulating our identity a little bit to make it look like what we want to make it look like. This is totally legal. Okay, so another way to say that the tangent of theta squared plus 1 is the secant squared of theta is just that the tangent squared of theta is secant squared of theta minus 1. So what can I do with this? I could take this, because it means the same thing as this, and substitute in here. And then notice we will be working with only secants in this equation. So I'm going to substitute tangent squared of x with secant squared of x minus 1, which gets us that the secant squared of x minus 1 plus 3 secant of x equals -3. I just did a substitution because I know these two things are equal right here. I'm allowed to just substitute secant squared of x minus 1 in using our identity. Okay, now I'm just going to make this look like a normal quadratic because I have the tools to do that. Adding +3 to both sides, I get that the secant squared of x, I'm going to rearrange a little bit, plus 3 secant of x, -1 plus 3 is +2. That is +2 equals 0. Cool, it's just another quadratic. It's something squared plus 3 something times something plus 2. I can factor this. Using the AC method, I know that I want things to multiply to AC, which is 2, and I want things to add to our middle term B, which is 3. 2 and 1, 2 plus 1 is 3, 2 times 1 is 2. So I know that this factors into the secant of x plus 1 and secant of x plus 2 equals 0. I want to solve these two factors for what they can when they're 0. So I'll do that over here. Secant x plus 1 equals 0. That happens when the secant of x is -1. I don't really know. I don't have my secants and cosecants memorized from the unit circle. So I'm going to think about this in terms of their reciprocal functions instead. If you remember, the reciprocal function of secant is cosine. And if we think about flipping -1/1 upside down, it's still -1. So we're looking for the cosine of x is equal to -1, thinking just about flipping it upside down. Where's the cosine of x -1, i.e. at what point on the unit circle is the x coordinate -1? That happens when x is equal to pi. Okay, so that's one of our solutions. Let's think about if the other one has solutions. We want the secant of x plus 2 to equal 0, which means the secant of x equals -2. Now, if we were working with cosines and sines, this should immediately be a red flag for you because, well, it's greater than negative, it's less than -1, it's greater than 1. That's a problem. That never happens. However, we want to work with the reciprocal. And if we think about -2 as being -2/1, reciprocal is cosine. So we are looking for the cosine of x is equal to the flipped version of this, which is -1/2. Okay, that actually looks a little friendlier. So at what points on the unit circle, at what angles on the unit circle, I should say, is our x coordinate, come on, is our x coordinate -1/2? Well, we know that happens right here and right here, about, which if you have your unit circle memorized, you'll know is 2 pi thirds and 4 pi thirds. So this happens when x equals 2 pi thirds and x equals 4 pi thirds. Cool. Those are our solutions in the principal interval. Now we just need to do our work with writing these as equations to include all integers. So right away we can see we have that solution at pi, 2 pi thirds, and 4 pi thirds. There's not really a nice way to condense any equations. We never have any nice jumps of by a factor of pi from terminal angle to terminal angle. So we just need to write 3 equations. It happens sometimes. So our set of all solutions is x equals pi plus 2 pi k, 2 pi thirds plus 2 pi k, and 4 pi thirds plus 2 pi k. Always remember, k is an integer. Any questions here? Okay. Let's do one more. This one's a little trickier, and you'll see why in a minute. I want to find all solutions of the equation just in the principal interval. I'm not going to really think about all the solutions here because we don't really need to. Let's just think about the principal interval. I want the negative square root of 1 plus cotangent of x is equal to cosecant of x. This doesn't really look like anything we've worked with before. There's 2 different trig functions. It doesn't look great. However, I think I can turn this into a quadratic. And how can I do that? Well, a legal algebraic move is to square both sides. Now, we'll have to think about things with the negative in front of the square root later when we get to solutions, because we could be messing with our domain here. If you remember from college algebra, square roots really affect our domain and what values are legal. So when we're done, we're going to have to check to make sure that our solutions even work. However, it is a legal algebraic move to square both sides. So I'm going to do that. So I know that negative square root of 1 plus the cotangent of x squared is equal to the cosecant squared of x, just squaring both sides. When I do that, I just get that 1 plus the cotangent of x equals cosecant squared of x. If you remember, that negative sign will go away when we square it, and that is where we're going to have a problem later, but we'll talk about it later. For now, we've done completely legal algebraic moves, and we can just keep going and try to solve this. Getting everything over to one side, I just get that the cosecant squared of x minus the cotangent of x minus 1 is equal to 0. Okay, again, I have a problem where I have a cosecant and a cotangent. I want to get rid of these. Because my Pythagorean identities usually have to do with the squared part of the function, I'm going to see if I can change that cosecant to a cotangent. Looking at my Pythagorean identities, oh, this is nice. I have that 1 plus the cotangent squared of theta is equal to the cosecant squared of theta. I'm just going to write that off to the side here. Hey, look, I have a cosecant squared right here. I have a cosecant squared right here. These two sides of the equation are equal, so I can substitute one in for the other. So instead of using cosecant squared of x, I'm going to use 1 plus cotangent squared of x, because that's going to be a lot nicer for us to solve this. So 1 plus cotangent squared of x, that's what we're using for cosecant, minus cotangent of x minus 1 equals 0. Simplifying a little bit, I just get that the cotangent squared of x minus the cotangent of x equals 0. I don't even need to do any factoring here because I see a common term I can pull out right away, and that is just cotangent of x, which gets us that the cotangent of x, pulling it out from both terms, just factoring it out, times cotangent of x minus 1 is equal to 0. Beautiful. We're already in factored form. We didn't have to do any complicated factoring. So we can just set each of these factors equal to 0 and solve. So first, where does the cotangent of x equal 0? Well, if you remember, cotangent is cosine of x over sine of x. We know that sine of x can be whatever. It's going to be 1 because we're on the circle, and the cosine will be 0. So where does this occur? This occurs when the x coordinate is 0. That happens here and here. And that is at the angles pi over 2 and 3 pi over 2. All right, that is the solution to that chunk right here. Let's check the next chunk. We want to set the cotangent of x minus 1 equal to 0. Therefore, the cotangent of x equals 1. So if you remember, cotangent is cosine of x, again, over sine of x. Now, the only time where the cosine and the sine are the same, i.e. we'll be dividing the same thing by itself to get 1, is when things are plus or minus root 2 over 2. But we also need them to have the same sign here because we're looking at a positive cotangent. So if the sine is negative, the cosine must be negative, and the cosine is negative, the sine must be negative. Remembering our quick little diagram here, which is always helpful to draw sometimes if we forget what quadrant things happen in. Oopsies. Our sine and cosine, i.e. our x and y values, have the same sign in quadrant 1 and quadrant 3. So we're going to be looking at the angles where that happens there. And that is actually right here. Here's pi over 4. Here's 5 pi over 4. So our two solutions are that x equals pi over 4 and 5 pi over 4, because those are the two places where both our x and our y coordinate are negative, or are positive and or negative root 2 over 2. Okay, so normally we would be done here. However, your college algebra radar should be pinging when you see this to say that, hey, there's a square root here. Our domain might be a little wonky. Like, as a quick reminder of what happens with that, let's just think about the equation negative square root of x equals x. I want to solve for x. I'll square both sides, get that x equals x squared because that negative will disappear when we solve. This is the same as x squared minus x equals 0, getting everything over to one side, which is factoring out an x, the same as x times x minus 1 equals 0. So our solutions here, we think, are x equals 0 and x equals 1, just setting this factor and this factor equal to 0. Okay, let's see if these work. Plugging our 0 in for x and plugging 1 in for x. Is the negative square root of 0 equal to 0? Yep, that's cool. That one works. Square root of 0, 0. Negative 0 is still 0. Cool beans. Okay, but what about negative square root of 1? Is that equal to 1? Well, the square root of 1 is 1. but -1 is not equal to 1. So, as you can just see from this little example here, we have some domain issues. This is not always going to work. As a result, whenever we're messing with a square root here, especially when there's a negative out front, we need to check to make sure our solutions work. We need to check to see if we have any extraneous solutions. So let's plug these in to our initial equation and see if they work. Start with pi over 2. So negative square root of 1 plus the cotangent of pi over 2 is equal to the cosecant of pi over 2. The cotangent of pi over 2 happens to be 0. So that is the negative square root of 1 plus 0, which is just -1. Cosecant of pi over 2 is 1. So we have negative square root of 1 equal to 1. But that means -1 is equal to 1. That is not true. So it turns out that pi over 2 is an extraneous solution. It doesn't work. We did nothing wrong in our algebra. Everything we did in our algebra was legal. It is just when we're working with square roots, we need to check for extraneous solutions. All right, let's check 3 pi over 2. Cotangent or negative square root of cotangent 3 pi over 2 plus 1. I wrote those in the wrong order, my bad. Cosecant 3 pi over 2. Cosecant 3 pi over 2 hold on. Sorry. Cotangent of 3 pi over 2 is also 0. So we have the negative square root of 1 plus 0. But the cotangent of 3 pi over 2 is -1. So we get that the negative square root of 1 is equal to -1, which means -1 is equal to -1. This one's cool. This one's a solution. Okay. Sorry, I'm running out of room here. I'll erase the stuff down here. This slide is not very well organized. Okay. What about -1 or negative square root of 1 plus the cotangent of pi fourths is equal to cosecant of pi fourths? What happens here? We have that negative square root 1, the cotangent of pi over 4 is just 1 is equal to square root of, or no, it's not even square root, it's the cosecant of pi over 4 is +2 over root 2, which multiplying the top and bottom by the square root of 2, we get 2 root 2 over 2, which is just equal to the square root of 2. So -1 plus 1, we get negative square root of 2 is equal to positive square root of 2. That is an extraneous solution. This one does not work either. However, I won't go through the math to check it because I think you guys get the point, but 5 pi over 4 does happen to work. So the only two solutions here are 3 pi over 2 and 5 pi fourths. I want to reiterate that we did nothing wrong in our algebra to get all 4 solutions. 5 pi over 4 and 3 pi over 2. Pi over 4, pi over 2 are still technically solutions, and they actually would have been solutions if not for this negative out front. But because that is what ended up making our answers wrong, as you can see here and here, those are extraneous solutions. So whenever you're messing with square roots, you do need to check for extraneous solutions. Are there any questions on this one? Okay, let's do a little review of something we already kind of know a bit, work with it a little bit, and then I will let you guys go for the day. You have definitely seen all of these before. I put this slide in here because it is A, nice to know the names of them, reciprocal and quotient identities, and B, not only is it nice, Alex cares that you know the names of the identities. Alex cares what the reciprocal identities are. And if you remember, you should definitely recognize those 3 and definitely recognize these 2. Those are how we defined secant, cosecant, and cotangent as the reciprocal functions of sine and cosine. It works the same here. You can do a little algebra to manipulate them to get that. You could just multiply, like for example, this one, you could multiply both sides by sine and then divide both sides by cosecant to get this one. These are essentially just the definitions of the reciprocal functions that we have already been working with. They just have a name now. They're called reciprocal identities. Also, we have the quotient identities that we've already used a lot, even in this class, where the tangent of theta is sine over cosine, and the cotangent is cosine over sine. These should look familiar. We've used them a lot. Questions? All right, I'm going to do one more thing that'll be a little bit of an introduction to what we're going to do next time, which is starting trig proofs. This is just a little foundation work for thinking about how we're going to do those. I want to use those reciprocal identities and maybe some other ones if they come up to simplify these three expressions. Now, we don't really know what they're going to simplify down to or how the simplification is going to work. So the best way to approach these is just to start basically throwing identities we know with them. What could possibly be useful? And 9 times out of 10, when you do that, beautiful things will happen because math is nice. So let's start with the first one. Secant of x times sine x over the tangent of x. That looks kind of nasty. The key here, or a good trick to always use when you're first starting out, is to try to put some things in terms of sines and cosines, or to try to make some things cancel. So just right up here in the numerator, I know that the secant function is the reciprocal of cosine. So I'm just going to start by rewriting secant as cosine because I don't like secant. It's a reciprocal function. It's not as nice to look at. So that means that this is equal to 1 over the cosine of x. I'm going to leave the sine of x and the tangent of x alone for now because they're not reciprocal functions. I don't care as much about them. Just to rewrite this a little bit, just to multiply this and this, I get that sine x over cosine x, just multiplying the 1 over cosine by sine, over the tangent. But if you remember, we have this quotient identity right here. This is the tangent is equal to the sine over the cosine. So I can rewrite sine x over cosine x as tangent of x. And anything divided by itself is just 1. Hey, that one worked out really nicely. All I had to do is I said, hey, I don't like this reciprocal function in here. The other two things are not reciprocal functions. What happens if I try to get rid of it? Another approach you could have used was you could have tried to turn tangent into sines and cosines as well. Maybe some cancellation would have happened there. That is always the key. I just didn't mess with the tangent in the denominator when I did it because I knew it was going to turn into a sine over cosine in the numerator, but it's always a good strategy to do that sometimes, especially when you're just starting out. All right, let's look at the next one. Cotangent squared of x times cosecant squared of x minus cotangent squared of x. Okay, this one looks a little scary, and I don't really think I have any identities right now that I can hit this with to do anything, but I noticed that in each of these terms, we have a cotangent squared of x. Let's factor it out. So that's the same as in cotangent squared of x. We factored that out, we've pulled it out, and now we're just going to write cosecant squared of x minus 1. Okay, now what do I want to do with this? Well, this should look familiar. If you remember, we have a Pythagorean identity that says that 1 plus the cotangent squared of x is equal to the cosecant squared of x. We have this Pythagorean identity. This isn't quite what we have. We don't have a 1 plus cotangent. We don't have a cosecant by itself. But if you look at this identity and subtract a 1 from both sides, we get that the cotangent squared of x is equal to the cosecant squared of x minus 1. Hey, that's exactly what we have. And it seems like because this is a cotangent out here that we have, it would be a lot easier to just get everything in terms of cotangents. So substituting this side in for this because they are equal, we have the cotangent squared of x times the cotangent squared of x, multiplying those two together. That is the cotangent to the 4th power of x. We can always write powers like that. We've only seen squareds so far because we haven't worked with any other powers. But whenever we write a power, we still write it in the middle like that. And that is as simplified as we can go. If we turned it into cosines and sines, which we technically could, it's legal, but I argue that that is a lot cleaner than this. We just want to get it looking as cleanly as we can. Doesn't need to be in terms of sines and cosines at the ends. It just needs to be simplified, and I would argue that this is the most simplified we can make this. Okay, last one at the bottom, we have the cotangent of x over the cosecant of x. These are not very nice. They're nasty. They're reciprocal functions. They're quotients. I'm going to turn them into sines and cosines because that's a good strategy, and maybe some things will cancel. Cotangent of x, if we remember from the quotient identity above, is the cosine of x over the sine of x. And cosecant, if you remember, is 1 over, it is the reciprocal function of the sine of x, so just use reciprocal identity, plug that in. I want to divide these two fractions, maybe that'll help. So to do that, I invert the second fraction or the bottom fraction down here and multiply by that. I just leave the numerator alone and I invert the top function or the bottom fraction and multiply cosine x times sine x in the numerator. And then the denominator, I just have the sine x. Those two sine x's cancel and I am left just with a cosine of x, which is pretty simplified. Questions on these? The premise of trig proofs, which is what we're going to start to get into next time, is I'm going to give you a point A and a point B. I'm going to say, hey, take this trig expression and make it look like this trig expression. So it's going to be very pointed simplification. These are the skills you're going to use for that. And I'm going to introduce a lot more identities that we're going to be using for those over the course of the next couple weeks. That is basically the premise of this entire unit, but it is these skills that you will be using. Which is why it's important to, in your ALEKS, make sure you're going through, reviewing your algebra and making sure you're comfortable with things like algebraic manipulation, solving quadratics, fraction manipulation, domains of things like square root functions, etc. That is why it is the largest ALEKS module, because it is very important that you help remember that stuff. Okay, I'm actually going to stop for today. We ended in a pretty good spot, so I'm happy stopping. I will release your next homework later today and we'll start getting on your grades. I will also have the answer key for homework 2 uploaded soon, and homework 3 will be uploaded today, like I just said. I will be around for a couple minutes, so you can stick around if you have any questions. Otherwise, have a fabulous Tuesday, and I will see you all tomorrow.